Hello, welcome to the Morin Red Book, Chapter 1 Problems, Section 1.3 Approximations and Limiting Cases, and Section 1.4 Solving Differential Equations Numerically. We're going to start with 1.1 Projectile Distance. A person throws a ball at an angle of her choosing to achieve maximum distance with speed v from the edge of a cliff of height h. Assuming that one of the following quantities is the maximum horizontal distance the ball can travel, which one is it? Don't solve the problem from scratch, just check special cases. So it's always good first to just draw the diagram. So here we have our height h, and then we have our little object, and it's going at speed v. Here I drew it horizontal, but in the problem they specified it can be at any angle, which is important later. And then we have this s of x max. So I wrote down all the possible ones, and you can just refer to the book for those. So first, we're going to start with the fact that g doesn't affect horizontal velocity. The greater the g, the faster the downwards motion, though. So this is because it's accelerating it downward. So it'll take it less time to hit the ground, right? So if we just write our basic kinematics equation, which relates distance, the initial time, and the acceleration, we have d equals v0t plus 1/2 gt squared. And because it's going down and we're not sure about the angle right now, we're just gonna put that the g is negative. So we're also, because of that, we're also assuming that our v0 or our vy is positive. So now we're just gonna solve for t, and now we're only gonna take the plus version, because in quadratic equation you get plus and minus. However, we're only gonna take the plus version because we want the time that's later. So when we see this, we can see that it has a negative 2gh and a negative g. So we're just gonna analyze that. So we see that's root g over g, which is equal to 1 over root g. So now we see that the time is inversely proportional to the square root of g. And the distance is directly proportional to t. This, we're gonna use that d equals vt. Um, so then we have that the s of x max is gonna be proportional to the square root of, sorry, inversely proportional to the square root of g. Okay, so now let's look back at our possible solutions. And we now know it can't be g h squared over v squared because then that would be directly proportional to g. So we've taken out 1. And now let's just look back at our equation that we solved for t. We can also see that it has dependence on h, meaning that there's an h variable that changes the amount of time. So we can see that because the s of x max also depends on t, the s of x max also must have dependence on h. So we also need to check that there is no quantity with no h. And here we see v squared over g has no h variables when it does have dependence on h. So going back to our diagram and just like thinking about what usually happens with like distance, we can see that if the velocity and the acceleration are constant, if you increase the height, you're gonna, or the distance that you have to travel, you're gonna increase the time, right? So then we realize that the height must be directly proportional in some way. Um, so we know that this quantity v squared over g over 1 minus 2gh over v squared can't be correct because the h is shown as inversely proportional. So then we can also see that if the velocity is 0, then the s of x max also must be 0 because all you'll have is a vertical change in motion, but you won't have anything horizontal to start with. So intuitively, you can't have any horizontal distance traveled no matter how much time you have. So now let's take the limit as v goes to 0 of the 3 that are left. So we can see that if the limit goes of v goes to 0, the square root of v squared h over g, that will go to 0. And you can just do that by plugging it in. However, for the next two, v squared over g times the square root of 1 plus 2gh over v squared and v squared over g times 1 plus 2gh over v squared, you have a v squared in the bottom. So what happens is the limit as v goes to 0 of 1 over v squared is going to be equal to infinity. And that is not something that we can use. So what we're going to do is we're just going to rearrange. So both of them, we're going to have the 1 plus 2gh over v squared. We're going to make the 1v squared over v squared. And then we're going to get v squared plus 2gh over v squared and cancel out things from there. And we see that the one with the square root goes to 0, but the one without the square root goes to 2h. So we know that v squared over g times 1 plus 2gh over v squared must be wrong. Okay, so now let's look at the last thing. We only have 2, so we need to cancel one out. So when h is equal to 0, all that happens is the cliff disappears. And you might intuitively think that if the cliff disappears, you won't have time, right? However, it does say that we can pick the angle. So when h goes to 0, all that happens is it becomes projectile motion. So the s of x max should not be 0. So now let's take the limit as h goes to 0 for both of these, and the limit as h goes to 0 of the square root of v squared h over g goes to 0, which is wrong. And then we have the limit as h goes to 0 of v squared over g times 1 plus 2gh over v squared goes to v squared over g. So now we know it can't be the square root of v squared h over g, so it must be v squared over g times 1 plus 2gh over v squared. This goes into some other stuff like actually solving it, but as you can see, the limit as h goes to 0 of the correct one goes to v squared over g. And this is actually the max horizontal distance for projectile motion. So that also enforces that we are right. Okay, so last problem, section 1.4, solving differential equations numerically. 1.7, two masses, one swinging. Two equal masses are connected by a string that hangs over two pulleys of negligible size, as shown in figure 1.6. The left mass moves in a vertical line, but the right mass is free to swing back and forth in the plane of the masses and pulleys. It can be shown, see problem 6.4, that the equations of motion for r and theta labeled in the figure are 2r double prime equals r theta prime squared minus g times 1 minus cosine theta, and theta double prime is equal to negative 2 r prime theta prime over r minus g sine theta over r. Assume that both masses start out at rest, with the right mass making an initial angle of 10 degrees or pi over 18 radians with the vertical. If the initial value of r is 1 meter, how much time does it take for it to reach a length of 2 meters? Write a program to solve this numerically. Use g equals 9.8 meters per second squared. Okay, now let's look at the diagram and try to understand this situation. So we have a left mass that is vertical, and it's going over a pulley tied via a string, then to the second pulley, and then it's tied to another mass, and that is making an angle. And the angle is 10 degrees with respect to the vertical. And this distance from this pulley to the mass is r. So now if we just analyze the forces that we have tension is along the string, right? So for this left mass, we can see that the tension is up, and then for this right mass, we can see that it's slanted up and then left. Okay, so now let's observe some properties of this. So for the mass 1, the two forces we have are the tension force up and the own mass one's weight force. And we can see both of these are in the vertical direction. So we know that because it also starts from rest, this mass 1 will only move in the vertical direction. However, for mass 2, we can't say that because the tension is slanted, so not vertical. And of course, we have the vertical downward gravity. We're going to write this mass 2 part in terms of polar coordinates, where that is our comma theta. And we're going to use that because it's more intuitive and it's easier to solve than doing it in Cartesian coordinates, which would be x, comma y. So we know that r is the length of the slanted right segment. And if the mass is closer to the system, then the r would be smaller, and if it was farther from the system, the r would be greater. And we're given the theta. So our key observation, which makes this more complicated than usual questions, is that the r is not constant because as the left mass goes up and down, we still have that the length is constant, so that will take away some of the length from the right mass. So this might seem like very complicated and stuff, but some key things that are kind of quite nice about this, we have that the masses are equal and the length is constant, so we don't have to worry about a lot of other things. So we're given two equations for our polar coordinates. So we're given the acceleration of r and then the acceleration of theta. So first, r with a dot on it is going to be r prime, which is the first derivative, and then the one with two dots is going to be r double prime, which is the second derivative. So we're going to start with r first. We're given that 2r double prime is equal to r theta prime squared minus g times 1 minus cosine theta. And we can see that this controls how the length changes. Okay, so first let's just look at some properties of this and try to understand more about this equation. So we first have this r theta prime squared kind of looks like a centrifugal force, and this just makes the motion more outward. And then we have this g times 1 minus cosine theta, and we can think of this as like a negative restoring force because when theta is positive or when its reference angle is positive, we'll have that this cosine theta will always be less than 1. So then that means that the negative g will, like, always be negative g. The most cosine theta can be is 1, so the only thing that it can be except negative is 0. So now let's look at this theta double prime. So we have that 2r prime theta prime over r minus g sine theta over r. So from this 2r prime theta prime over r, we can see that this acceleration of the theta is caused by the length changes, which is kind of interesting. And then we also have that negative g sine theta over r. This is also a restoring force. So we're also gonna say when theta is positive because usually you're not gonna go over 90 given this system. So sine theta is gonna be in the bounds of 0 and 1. So then that's also gonna be negative. And it's kind of like a coupling term between the radial and angular motion. So, just another reminder, the initial conditions are given, so it's at rest. So now let's think of that in terms of the equations. So we have r prime of 0 is equal to 0, and theta prime of 0 is equal to 0. Then again, in terms of the equations, r of 0 is equal to 1 meter, and theta of 0 is equal to pi over 18 radians, or 10 degrees. So now what is it asking you? It's asking if you start at t equals 0, or the initial conditions, what time will you be at r equals 2? So now, if you look at these set of equations, we have r is depending on theta, but theta is also depending on r. And then we have these like weird products like r prime, theta prime, and then we also have these trig functions. So this system closely resembles a coupled nonlinear differential equation. And these are very hard to solve, so and you can guess why because they're all like very intertwined, right? So what we'll do is we'll solve it using Euler's method. So Euler's method is just a way of approximating ODEs or ordinary differential equations. And what we'll do is we have the starting r and theta and the um, equations, making that r prime and theta prime at that instant. So we'll use that and we'll then update the velocities, r prime, theta prime, and then the positions, and then we'll go back to updating the r double prime and theta double prime, and then we'll keep repeating these steps. And it can be intuitive to think that the more times you repeat, the more accurate you are, so the smaller the step. So here in the graph, you can see in this red and pink, we have these bigger steps, and you can see that it's not as accurate. But then if you look at this purple and light blue, you can see it's pretty accurate, and the function is the dark blue. So the formula for Euler's method is y of n plus 1 equals y of n plus delta x of f of x of n comma y of n. So while you might be able to do like maybe like 1 to like I don't know 10 or like maybe like 10 to 20 if you're like very passionate about this, you'll like often need a lot more. So that's why you're going to use code because it can just brute force everything. So let's look at Morin's code. So first what he does is he writes all the givens, and we do need that given Euler's method. Okay, and then for this E part, he's just writing the interval. So he's making the delta x in the Euler's equation very small so that he can be more accurate. And then he's having this thing that says y while r is greater than 2 do this. So this is the stop condition because we're given that we need to stop when the r reaches 2. So this is saying like the second it's more than r equals 2, just stop. Okay, so now all he's doing is he's putting in all the equations. Yeah, so now they're looped in, and that's how they're going to update everything. And it's saying that at the end, when r is equal to 2, that's when you stop. And you see that it says that print of the value of time is equal to I times E, which makes sense that because it's the number of steps times the step size, which is the time in seconds. And again, the smaller your step size, the more accurate you'll be, and it kind of just depends on how precise you need to be.